Okay guys, so you've already mastered the graphing of the sine curve, so now we're moving on to the cosine curve. So go back to the first page of this note, the graphs of sine and cosine, and recall that we can represent theta on the Cartesian plane. Okay, here, theta. So in this case, when you drop down and make your right triangle, this is x, this is y, and this is r, cos, so katoa, cos is adjacent over hypotenuse. So the x value is adjacent to theta, and r is the hypotenuse. Okay, so an xy can actually be represented as cos theta. Oh, sorry, no, that's later, but I can do that. Okay, so you just need to fill in this x over r here. So when we go down to the unit circle, again, now our r value is just 1, okay? This is just 1 here. And so if this is theta, and this is x, and this is y, cos of theta is x divided by 1, which, of course, is just x. So since cos theta is x, we can rewrite this coordinate as cos theta, and y is sine theta, so cos theta, sine theta. So that means that any coordinate on the unit circle can be represented with cos theta, sine theta, because the x's are just the cos thetas, and the y's are just the sine thetas. Pretty cool. So we're going to use the exact same logic we used in the sine curve video to develop the curve of cosine. So if you're still having a little bit of trouble, hopefully this might help clear things up. And if you really understand the stuff, hopefully it just helps to cement your current understanding here. So again, we could do this the traditional way by doing a table of values. Okay, so if you do cos of 0 into your calculator, you'll get a 1. Okay, you can try it. If you do cos of 90, you'll get a 0. Cos of 180, you'll get a negative 1. Cos of 270, you'll get 0. And cos of 360, you'll get 1. Okay, so again, I could just plot these points. No harm, no foul. But I'm not going to. And then cos of 45 degrees, you would get 1 over root 2 is the exact value. Here you'd get negative 1 over root 2. Here again, a negative 1 over root 2, and 315, a 1 over root 2. So I could plot these, you'll see what happens. But let's do the logic of what's going on here. So remind yourself, while you're doing this, that cos theta is just equal to x. Okay, it's just equal to x. So as we go around the unit circle now, we're going to be considering how is x changing, what are the values of x, and whatever the answer is to that question also answers the question, how is cos theta changing, what are the values of cos theta. They are equal, so that means the same thing. So let's label the coordinates again. So remember, this is a unit circle, so its radius is 1. So x, y, this is 1, 0, this coordinate. This coordinate is 0, 1. Here we have negative 1, 0. And finally 0, negative 1. So now today we're paying attention to the x values, not the y values, the x values, because that is equal to cos theta. So as theta is going from 0 degrees to 90 degrees, okay, cos theta, okay, starts at 1. Okay, think about what's happening to our x values. So as we go follow this circle, think about the x values, not the y values, but the x values. So how far we move horizontally left or right. So we're actually decreasing. Our x value is becoming less and less because we're going in the left direction, in the negative direction. So our x value at 0 degrees is 1. This coordinate here is 1. And our x value once we get to 90 is 0. So cos theta is decreasing from 1 to 0, okay? And that's the same as what the x's are doing, okay? So cos theta is the same as x. So you can write here, because x is decreasing from 1 to 0. Okay? I'm only going to write that once so I don't have to make it look so crowded in each of these quadrants. But cos theta is doing this because x is doing this. So we start at 1. Okay, make sure you have this labeled. Okay, 90, 180, 270, 360, going up to 1, down to negative 1. I used 1.5 centimeters to get up to 1, just so it was spaced out a bit. So we're going from 1 down to 0 in the first 90 degrees. That's what's happening. Okay, then we continue on. Now theta is moving from 90 degrees to 180 degrees. So theta is moving from 90 degrees to 180 degrees. What's happening to our x values? Well, they're continuing to go in the left-hand direction. So they're decreasing from 0 to negative 1. From 0 down to negative 1. So cos theta is decreasing from 0 to negative 1. Okay, so we're starting at 0, and here we're decreasing to negative 1. Okay, now remember, this shouldn't look like a straight line. It is a curve because the rate at which it's decreasing is not constant. It's not going down by a constant amount. Okay. Then we have here, so now we have theta moving from 180 to 270. Okay, and cos theta, or our x value, is now increasing because we're moving in the right direction, or in the positive direction. Okay, so it's increasing from negative 1 to 0. So here the x is negative 1, so cos theta is negative 1. Here at 270 degrees, x is 0, cos theta is 0. So we're increasing up to 270. And finally, we complete our revolution. So theta is increasing from 270 to 360 to 360. And cos theta continues to, increase. It's going in the right direction. So it's increasing from, here our x value is 0, here our x value is positive 1. So at 360 it'll be positive 1, so it increases to positive 1. So this matches the table of values we created initially. It matches our understanding of cos theta being equivalent to any of the x values in the unit circle. Okay, and it creates a periodic function. So these are the 4 kind of sections that represent the 4 quadrants of the circle, and these will keep repeating as you go around the circle. Take a look at that. You can pause it, make sure you get it all. So you should be thinking about things like, how would I describe this to a friend? How would I describe this to someone for the first time? Okay, that's what I'm looking for when I'm testing your communication and your understanding. All right? So, again, this is the same as last time. We can extend by continuing the cycle around the circle. So cosine at 0 is up at 1, then down to 0, down to 180, and then back to 0, and back to 1. So this is one cycle when it is already back up at 1. Okay, and then it does the same thing again. Starts at 1, down to 0, down to negative 1, up to 0, back up to 1. So here's another cycle that goes from 360 degrees to 720 degrees. In the negative direction, we follow the curve back this way. So at negative 90 degrees, we would be back at 0. At negative 180, we would be down here at negative 1. At negative 270 at 0. And negative 360 is back at positive 1. Okay, so there you go. That's 3 cycles of the cosine curve. thinking too, how does this relate to the sine curve? What's the same, what's different? So many of our key features are the same. However, there are a few differences. Okay, first of all, the period is the same. It takes 360 degrees to complete one cycle. And that's because you're going around the circle, the unit circle, right? And a unit circle has 360 degrees. The maximum value here is still 1, with the minimum value of being -1. Our axis is still y equals 0. And our amplitude, what is it? Think about it. Still 1, okay? Because that's the distance from the axis to the maximum or from the axis to the minimum. Either one, okay? Now, our zeros do change. In this case, they're 180k minus 90 degrees, where k is an integer. You can use that formula to find the 0, okay? Your domain is still anything, so theta is in a set of all real numbers, and your range is still between -1 and 1, where you include the -1 and the 1. And it can be any real number in between -1 and 1. So, when sketching the sine curve, remember the 5 key points, and continue to create cycles by just adding 1 period to each point. So pick a point, add 360 degrees to it, and then you can plot another point. Pick a minimum, add 360 degrees, you'll find another minimum. Add another 360, you'll find another minimum, okay? Multiply 7 times 360, add that, you'll get another minimum, okay? So every 360 degrees, the exact same points repeat again. So they're very, very similar. How are they related? Think about this. How is this related to sine? Well, a sine curve, excuse me, a sine curve, the difference is with the sine curve, it starts, okay, its y-intercept is at 0. So in other words, its y-intercept is on the axis of the curve, okay, here on the axis. A cosine function, however, starts, or its y-intercept is at the maximum, okay? So either you can think about, this is a sine curve that's been shifted 270 degrees this way, okay? So why doesn't it just start here if it's a sine curve? You can say, oh, well, here's 0, so it's just been shifted here. Well, no, because here it starts at 0, but then it goes down. A sine curve starts at 0 and then goes up. So it's been shifted 270 degrees to start here. Or you can think about it that it's been shifted 90 degrees to the left. Because if you continue this, right, there's that's negative 90 degrees. This is the beginning of a sine curve, okay? So you also think about that a sine curve has been shifted 90 degrees to the left to create a cosine curve. So why do we have 2 options? Well, that's just the nature of periodic functions. Because they repeat, you can either translate one way or the other way in order to find the same repeating function, okay? So that's just something to kind of keep in your back pocket. So now we just have one example. It's very similar to yesterday's examples. It's just that now we have a cos instead of sine. So really it just means you're using a different button on your calculator. Okay. But the other difference with this word problem is that it's within a real life situation. Okay, our questions yesterday just were like sine equals this, and they had no meaning. Here we have actually the height of a basket on a water wheel. So first I'm going to do something really silly and draw a water wheel. It's silly because you guys all know I can't draw, but I'll do my best, okay? So here's a water wheel. Okay, you have a little basket on it. Pretty bad, I know. And basically we're doing its height above the water. So spoiler alert, the water line is exactly halfway through the circle, okay? You'll see why in a second. So here's the water. So the height of the water here, or the height above water, is 0, okay? And we have a cosine function, so that means when t is 0, it's going to be at a maximum. Think about that. Because we're using a cosine curve, okay, when t is 0, the water wheel will be at a maximum because that's a feature of a cosine function. So we're actually going to be starting here. So in other words, t equals 0. Okay? And then it's going to be cycling this way. Okay? So let me think. If we were finding the, see how this has a degrees out here? So we have to multiply the time by 6 to get the degrees. So to show one cycle of the cosine curve in terms of degrees, we could put 0, 90, 180, 270, and 360, okay? That's what we would do in order to find the degrees. But how do we find the time? So for instance, if I have 90 degrees, how do I get from there back to time? Well, 6t is 90 degrees, so t is just 90 divided by 6. So to go from 6t to t, you just divide everything by 6, okay? So to go from here to here, I would divide by 6, or to go from here to here, I would multiply by 6. So my first time is 0. My second set is 90 divided by 6 is 15. 180 divided by 6 is 30. 270 divided by 6 is 45. And 360 divided by 6 is 60. So these are the degrees, which is what the cosine function needs to be able to put in the calculator. But what the function does by putting 6t is relates that back to time in seconds. So we're using degrees, we're manipulating degrees to get to the time that we actually want. Okay? So I chose 0 to 360 because I know that's one cycle. And so one cycle in terms of time is from 0 to 60. So that means the period is 60 seconds. That's how long it will take to go around the water wheel one time, is 60 seconds. So then what is h of t? So h of t is cos of 6t, and 6t is whatever this is in this column. So cos of 0, we found out before, is 1. You can still use your calculator if you need to, okay? Don't be embarrassed if you need to use your calculator, but you can also just use the unit circle, right? And at 0 degrees, the coordinate here is 1, 0, and you just look at the x value, okay? Again, the cos of 90 degrees, this coordinate is 0, 1 on the unit circle, and cos is just x, so cos here is 0. Here it's negative 1, 0, so cos is negative 1, then 0, and then back to 1 again. Okay? So that means my little water wheel, it has a maximum height above the water of 1 meter. So at 0 seconds, that's when they started timing it. It's at its maximum. It's 1 meter above the water. So this here is 1 meter. Okay? Then at 15 seconds, it's hitting the water. Okay? At 30 seconds, it's 1 meter under the water. Okay? At 45 seconds, or 270 degrees, we're at 0, so it's at the water level. And then after 60 seconds, it's back at its maximum again. So this is one cycle. We can continue and draw a second cycle by just following the pattern. So another 15 seconds, so that's 75, we're at the water again, then down, then up, and then back to our maximum at 120 seconds. So here's what's going on with the water wheel. Okay, so this is time in seconds, and this is height in meters, okay, above the water. So notice that the period here is 60. So this means that the basket completes one cycle in 60 seconds, okay? That's what that means. Okay, and also notice that the basket starting position is at the top, so 1 meter high. Okay, think, how would this have changed if the function had been a sine function instead of a cosine function? Where, in this little picture of the water wheel, where would we have started? Okay, so it would have started on the axis, being ready to increase. So here isn't right. This is the axis, but it's ready to decrease. A sine curve would start it on the axis, ready to increase. So this would have been the start if it was a sine function. Okay? So make sure you understand that whole thing about how you're converting degrees back to seconds. Okay, that's going to be important coming up when we're doing the modeling and all the word problems. And this is the most basic example. So let me know or rewatch that little section where I explained this. Make sure that you take that as a priority, is understanding that conversion, okay? So now we just have two things to do with the equation. So one is finding the height when given the time, and one is finding the time when given a height. Pretty typical math questions, right? So in this case, height, we're given the time, so we sub in 15 for t, or 14 for t. So really we're just finding h at 14, so we're just subbing that into the formula. So that's the cos of 6 times 14, okay, degrees. Make sure you're using the double brackets there. And you put that into your calculator, you get 0.1. So therefore, at 14 seconds, basket is 0.1 meters above the water. Okay, and that should fit back with your graph. Okay, that's right before 15 seconds. 15 seconds is where it hits the water on its way down, so it makes sense that it's just right above the water level. But now, when will the basket be 0.5 meters underwater in the first minute? Okay, so this is answering the question h at t equals 0.5 when t is between 0 and 60, okay, because it's in terms of seconds, so we have to turn that minute into 60 seconds. Okay, so if you look back at the curve, okay, I don't have it anymore, but if you look back at the curve and you pick 0.5, you can trace over and see that there's two spots where we're 0.5 meters above the ground. Okay, it's going to be, well, you'll see where it is. Okay, oh, sorry, I just made a mistake. Underwater. Underwater. So that means the height is negative 0.5. Read carefully. Okay, negative 0.5, because we're looking underwater. So now look at negative 0.5. If you go across, you'll see there's, in the first minute, there's two sections where